Hello, I'm Enzo Carter, and I want to say sorry for not uploading in a while. I was just being kind of lazy, but Enzo Science is back. In this video, I would like to talk about artificial intelligence, and specifically neural networks. Before I go into the specifics of what those are, I have to talk about what artificial intelligence is. Essentially, it's using a computer to replicate human tasks. That's the extremely brief oversight. And one of the ways humans do this is with neural networks. Originally, we just made if-then statements, which worked for a while, but then stopped working once the problems got more complex. So we started using algorithms. The one I'm going to be talking about now are artificial neural networks. I'm going to start with just laying out the basic structure and anatomy of a perceptron. Before I go any further, a neural network is used in your brain. That's how your brain thinks and such. And we took that design, modified it significantly, and that's what we use as in the field of artificial intelligence quite often. So a perceptron is the most basic form of artificial neural network. It's just one neuron and maybe just a few inputs. And I'm going to draw a little picture with my terrible handwriting so you guys can see what's going on. And then I'm going to talk about it. Okay, so we're going to start on the left side of this image. Essentially, what you're seeing there is the inputs. We can't really control these. This is just whatever we're feeding into our network. Now, they're labeled as x0, x1, x2, and they're matrix. Now, that matrix is added with the weights. The weights are the W0, W1, W2. Essentially, you add those two together. That's what the sigma notation represents, the adding of the inputs and the weights. Now, after you've done that, you need to pass it through a nonlinear function. Now, a nonlinear function is a function that is not linear. Essentially, using a linear function, just passing the data forward, makes it very difficult to map to any data that's not linear. So using a nonlinear function allows you to map to data that's not linear. Good. So a nonlinear function, in this case, at the top, you can see the ReLU activation, which is just the max of 0 and x. Essentially, if the value is greater than 0, they get just passed on normally, as if it was a linear function. And if it's less than 0, if it's a negative number, they get passed on as 0. The function on the bottom is the sigmoid activation function. Sigmoid function was originally used because it replicated the brains. The brain doesn't have an activation function, but it's an activation-like system where the neuron is either on or off. The sigmoid replicated that, but the sigmoid's kind of slow in terms of computational efficiency, and bigger models are going to be running this activation function at least several times per second. So it needs to be pretty simple. So the ReLU is usually the one that's chosen. But I wanted to add the sigmoid just to add a little bit into the history of what we used to do. Now after this, you'll notice the plus bias. Bias is more or less another knob to turn along with the weights, and it's a unique bias for every neuron, because you can think of this as just a building block. If you add a bunch of perceptrons together, you can get a more complicated neural network that can do better things. But of course, the neural networks that are actually doing serious stuff, like classifying images in the best way, are working much more differently. I might talk about that in a later video. The bias you can think of as moving the activation function around. So the tuning of the weights makes some function to fit the data, and the bias moves that function onto the data. That's the best analogy I have. It's not great, but it kind of works. Hello? Now you probably want to know how to code one of these things right about now. I mean, they're really cool to learn about, but if I can't program one, what's the point? So I'm going to show you that now. I'm using Collaboratory. It's a Jupyter Notebook-like web-based IDE by Google, usually used for deep learning research, but you can use pretty much whatever you want. They all work. And I'm going to use a couple APIs. First, TensorFlow. And Keras. Along with NumPy. And then I like this because then you don't have to re-import the big TensorFlow library every time you want to do something. But essentially, next, I'm just going to show you how to make a simple MNIST classifier, which is the hello world of machine learning. So after you've got these inputted, the next thing you're going to do is make the model. In this case, a Keras.sequential, or a sequential model by Keras. Okay, model equals Keras.sequential. Now this is like a stack of layers, essentially. So we're going to start with the import layer, which is going to consist of Keras.layers.inputs. That's what it is. This is going to have a shape of 784. Now what does that mean? Shape equals 784. Is that just, what is that? Essentially, we're feeding this neural network a 28 by 28 pixel grid. Now this pixel grid can't be read by the neural network as a picture. So we have to condense it down into one little string of the grayscale values for all the pixels on it. And that's what this represents, a 784 digit long string. Next, we're going to want some things called hidden layers. These are the little thing that contain the x where you did the nonlinear function. Dense. These are called dense layers. Means they are every neuron in the layer previously is connected to every neuron in the new layer. Everything's connected, essentially. In actual image processing, you would use a convolution neural network, which I will talk about later. So this dense network is going to have 16 neurons. It's pretty arbitrary. Just going to put something on there. You can play around with it and find the right thing. Basically, this is the first thing you put here is how many neurons or units, and then you can put the activation function. And we're going to use ReLU because it's faster than the previously listed reasons. We're going to put 2 of these. Actually, let's do 4 of them. I think that's what's usually done. And then at this point, you can essentially copy and paste this, because they're going to be the same no matter what. You can play around with different sizes. You could make them different sizes if you wanted to. You just have to play around with it. And then the next is the output, which is going to be another dense layer, just like these ones. But one notable difference, it's going to have 10 units, and its activation, the biggest change, is going to be softmax. Softmax is usually used in outputs of classification models such as this one. And then at the bottom here, we can put model.summary. Oh no. Did I misspell something? Give me one moment. Okay, so I said inputs here, Keras.inputs, not input. it's just, oh shoot. I misspelled something, my bad. Hey, okay. So as you can see here, it lists all the parameters of our neural network. So you can play around with this. We can take away one of the layers if we wanted to. Everything still works just fine. Or I think I'll leave it like this with just 3 of these hidden layers. Alright, next we need to train this model. So first we need a data set, well, which today we're going to use MNIST. X train. Alright, so this error basically says that I put this in the wrong order. So MNIST goes right here. So it's datasets.mnist.loaddata. That makes more sense. Okay, it's here. Now we need to reshape it to be the proper shape. As type float 32. Okay, so what I'm doing here is I'm taking in the just training data. I'm just basically grabbing the entire data set, and now I'm basically organizing that data set. Shape. Alright, essentially I have 60,000 individual different images, each one with 784 pixels in the little string, so that way it can fit in this input layer here. And I have 10,000 test images, which basically checks to see if my training was accurate. Next we use the model.compile function. Loss equals curious dot sparse categorical plus entropy from logits equals true. Now I would tell you what from logits equal true means, but I'm not entirely sure. All you need to know here is that loss function basically tells the network how good or bad it's doing, and then it takes that value and upgrades itself with the optimizer. It optimizes its performance with oh shoot, why did I put a space there? Curious.optimizer .rms prop. What's this? Oh. RMS prop. And then metrics equals it's not this, it is just accuracy. Okay, this should work. Please hold. Okay, so yeah, it's optimized. Curious.optimizer is not curious.optimizer, and this runs well. Last and final thing is model.fit. This is when we actually pass in the training data for it to run. We start with the training data, and then the thing to validate the training data, which is ytrain, and then batch equals Now wait, what's batch size? So essentially, Y-train here is basically the samples, is the label for the samples. So our samples are here. It's going to see one of these. The neural network is going to see one of these, make a guess, and then it's going to test that guess with the label. If it guesses that a 2 is a 3, then it's going to find out that it did it wrong because it looks at the label. And then it's going to calculate a loss function with categorical cross entropy. And then the optimizer is going to adjust the little weights we saw before in order to get better accuracy and better loss. So metrics equaling accuracy, that's just for the person training it to get an idea, because accuracy isn't that good for the network when you're training it. Basically, if you replace loss with accuracy entirely, would not go well. So what's batch size? Batch size is how much of the data you're showing the network at once. You could show the network one data point at a time. The problem with that is the training goes very slowly, and adding higher batch sizes is better. So essentially, it's usually either 16, 32, 64, or even as high as 128. Let me get something running. I'm going to use 64 here. And then after batch size, we have the validation split. Now the validation split is how many. The validation split is how much of the test data, or basically the validation split is you're taking some amount of the training data and giving it to the network, but you never show that training data to the network. Essentially, it's some data the network's never seen in order to see how well the network's actually doing. And then epochs goes right here. Epochs is how many times you're gonna go through, how many training cycles. Let's do 2. Basically, adding more epochs trains it more, but eventually you can't train it anymore, so there's no point. And then, yeah. So let's turn it on. Alright. So essentially what all this means is that the first epoch, we had a loss of 0.6 and accuracy of 0.8. And you'll notice the validation loss and validation accuracy vary. That's because it's not seen that data before. So it's going to act differently to it. And then the final epoch, the epoch we actually care about, we have a loss of 2.26 and an accuracy of 0.92. So it classifies 92% of the images correctly. That's pretty okay, considering we just kind of randomly guessed with a lot of these inputs. I mean, and what you would actually do is you would play around with these, maybe increase the amount of neurons here, and maybe a lower batch size, an extra epoch. You would play around with it a little bit. Let's see what it looks like now. And now we actually did a little better. We got 93% final accuracy. But as you can see, the validation stops really changing after the first epoch, so additional epochs are not entirely necessary. So if we had one epoch, it's essentially the same. Oh, and you'll see here that the validation accuracy is slightly lower than the regular accuracy, and the loss is higher. Now, higher loss means the model's doing worse. This is something called overfitting. Essentially, the model trains too much and ends up just memorizing the data, which we don't want, so then it does poorly on unseen data. That's all for today, folks. Goodbye. Thank you for watching. Please let me know if you like this content and want to see more neural network type videos. And of course, like if you enjoyed. If you did not enjoy, please dislike the video and tell me what's wrong in the comments. I love to hear your feedback.